one of the most important numbers to know about an electric device is how much energy it's going to use, how many joules, since ultimately that's what you're going to be billed for by the electric company. But they can never tell you that when you're buying a device, because they don't know how much you're going to use the device. If you use it a little, it's going to use very little energy. If you use it a lot, it's going to use a lot. So the best they can tell you, the most important thing to know about a device, is its power. Remember that energy, joules, is related to power in that power is the speed of energy. The watt is really the joule per second. So if you want to know how much energy a device is going to use, you just multiply the joules per seconds times the seconds you use it for, and you end up with joules. So as we study electricity, we're much more concerned with power, the speed of energy, than we are with energy itself. So in this unit so far, we've learned about another speed, this new thing called electric current, in other words, the speed of charge. And I'm going to give a hypothesis, and I'll demonstrate in a second, that the power, the speed of energy, is proportional to the current, the speed of charge. Now I'd like to show you what I mean by that. So I'm going to use these ping pong balls to represent electrons flowing through a circuit. Instead of electrons going to a device, my ping pong balls will be delivered to the chalkboard, and they'll be doing work on the chalkboard, making tiny little dents in it that we can hear the noise of that being made. So if I'm going to claim that current, how fast charge moves through a circuit, affects power, how fast work is done, I have to justify that somehow. I think it's pretty easy to see with ping pong balls. If I throw the balls infrequently, work's not getting done very fast. There's not much flow of ping pong ball, and so any change to the board is happening very slowly. Contrast that to if I start throwing frequently. Change is happening pretty quickly because the balls are hitting the board much more often. So clearly the frequency at which I throw the ping pong balls is very important. So we just justified how power, joules per second, must be proportional to current, coulombs per second. The more frequently charge reaches its destination, the faster work is being done. But this is not an equal sign. If we wanted to turn this into an equation, we would have to say something like power equals current times some constant. And what would the units be on that constant? Well, let's look. We've got joules per second for power. We've got coulombs per second for current. So if we wanted these to be equal, the units on our constant have to be, well, on top I have joules here and coulombs here. So I must put joules there so I can get joules on top somehow. Now, it turns out I don't want coulombs on top, which I'd have here. So to get rid of them, I have to put that on the bottom. So if I have this unit joules per coulomb, then coulombs cancels, and I end up with power. So this new constant must have the units joules per coulomb. So what would that mean? That's how much energy charges are carrying through the circuit. Not how much total energy goes through, but how many joules per unit of charge per coulomb. So that's a really important unit. It's so important that we give it its own name. We call the joule per coulomb which is really an energy, say potential energy, divided by a charge. We call that this new unit V, where V is usually called electric potential by scientists and voltage by everybody else. And apparently, the power of an electronic device is equal to the frequency at which charges flow times this new quantity, potential or voltage. So we need to now justify why the joule per coulomb, the electric potential, should have anything to do with power. I'll use the ping pong balls again. You know that how frequently I throw the ping pong balls, the ping pong ball current representing the electric current, affects how quickly the board gets energy. But what else matters? How hard I throw them. In other words, how much energy does each ping pong ball get? So if I do kind of a wimpy shot at a certain frequency, I'm not giving the board all that much power. But what if at the same frequency I really winged the ball? Whoa, didn't expect that. If I really throw the ball fast, each individual charge hitting the board is going to have more of an effect. And that's the energy per charge. That's the potential, the voltage. So those two things together, how frequently does a charge arrive and how much energy does each individual charge have, that's what's important in determining how quickly a device uses energy. We need both in order to figure out what's going on. Electric potential, or voltage, is one of the toughest concepts for students to understand. It's not clear that up till now we've just talked about energy, why we now need to talk about energy per charge. Well, the reason for it is that we don't know how much electricity is going to flow, since we don't know how long a device is going to get used for. But it's really important that the energy arrives at that device at the right speed. I think you can imagine that when I was throwing those ping pong balls before, there's probably a maximum speed at which I can throw them before I start breaking stuff. So a device can only take a certain amount of energy per charge carrier. And if you start to exceed that, stuff gets broken. Best example to give on why this is important is to compare electric potential or voltage to water pressure. So I've drawn here a water tower, and I've drawn here a house. And out in the Midwest, where there's not a lot of mountains, the way you cause water pressure is you put a water tower up, which is a lot higher than the surrounding buildings, and you store the water up high. And then as it falls, it presses down on itself, it gains kinetic energy, and it comes out of your tap with a certain speed. In more mountainous areas, like here in Connecticut, we usually accomplish this by putting reservoirs up high, so that the water supply is still up high. But if you don't have mountains, you need water towers. So let's say the town you're in starts growing, and they want water to go at the same speed it's always grown at. What do? You start putting in more water towers. And you make them all the same height. And that'll give you the kind of constant pressure you need to make sure water always comes out of the tap at the right speed and that it doesn't damage stuff. But what if you wanted the water, every drop of water, to have more energy? Those 3 new water towers, where could you have put them? You You could have put them right on top of the original one. So what would that accomplish? Well, every drop of water now would have more potential energy. Every drop of water originally only had that much. Every drop now has this much. And it doesn't matter how much water comes out. Every drop of it arrives with that much potential energy having been converted into kinetic. So we control for the fact that we don't know how much water is actually going to flow by just dividing by the amount of water. When it's electricity, we divide by the amount of charge. So potential is kind of like the pressure the water comes out at. Every drop of water has more potential energy to begin with, comes out faster. That's how we can understand why electrons flow faster, current flows faster, when you have more electric potential or voltage. There's been a lot in this video, so I just wanted to end with a quick summary. When we're talking about energy with electronic devices, since we never know how long they're going to be on for, it's power that we know about. We want to know how much energy they use, we multiply their power times time. And if we want to know about power, we need to know two things. First, how frequently do the charge carriers arise? And that's what electric current is, the speed of charge. And then also, each of those charges, how much energy does it have? If you combine those two together, you know how fast energy arises at that device. So as we go forward, we'll use all of these concepts, but we're always going to pay attention to power, because ultimately if we want a device to do something, that's what we have to care about.